Yes, so recording started. So rate monotonic scheduling. Actually, this algorithm is coming under static scheduling algorithm. Static scheduling means before the system starts, you will be doing all the pre-processing and let the scheduling runs as per the scheduled order. But in between, if any new task join the system, this scheduling does not know how to handle it. So it is a static priority scheduling. So generally static priority scheduling. So the priorities are fixed during compile time, not during runtime. Okay, so this is one algorithm generally called as RMA, RMS, or RM algorithm. Another algorithm called as earliest deadline first. Generally we call as EDF algorithm. So EDF algorithm, actually it is the practical difficulties are very high in EDF algorithm, which is practically impossible to implement it. But anyhow, this algorithm, it is a dynamic priority algorithm. Dynamic priority algorithm. So dynamic priority means the deadlines with the earlier deadline, the task with the earlier deadlines will have high priority. The later deadlines will have low priority. So this is what we call earliest deadline first, EDF. Another thing is rate monotonic scheduling. Okay, so usually what happens is these two algorithms actually, if you take Chandrayaan 2, then Mars Pathfinder, and any space shuttle. So whatever embedded systems they develop with, high-end embedded system solutions, most of the embedded system might have this RM algorithm, rate monotonic scheduling. So it is a specialized algorithm, generally useful for real-time systems. So even in the temperature controller inside a aircraft, the aircraft cabin or cubicle, and the nuclear reactor, the nuclear breeder reactor, something the control system inside. So in most of these aspects, this rate monotonic scheduling will be one of the algorithm to be implemented. So generally, it's under static priority scheduling. EDF, it is generally for understanding EDF is fine, but there are many difficulties in implementing the EDF algorithm. So maybe once we see one schedule, we'll understand how really it happens. Okay. So both these algorithms are optimal algorithms. So generally, both are called as optimal algorithms. Both the above are called. So EDF and RMS both are called as optimal algorithms. So what is meant by optimal? What is meant by optimal is uh, if an optimal algorithm fails to produce a feasible schedule, then no other algorithm can schedule it. Okay. So what does it optimal algorithm means? If an optimal algorithm fails to produce a feasible schedule, then no other algorithm can schedule the task set. Okay. Now, for example, if I give a task set which is not been scheduled by an RM algorithm or an EDF algorithm, then I ask you to do schedule in some other algorithm, then no other algorithm can able to do that. So that is called as the optimal schedule algorithm. But there are optimal uniprocessor algorithms. So uniprocessor means only one processor this algorithm in. So okay. So multiprocessor, anyway, we are not going to touch upon multiprocessors. Just uniprocessor scheduling algorithm. Just only one processor. Okay. Now the assumptions here. Assumption here is all tasks in the task set are periodic. So generally it is periodic. Generally for RM algorithm. So this is mainly for RM algorithm. Assumptions for RM. Okay. So then the relative deadline is equal to the period. The relative deadline is equal to the period. So these are the assumptions that we usually take Suppose if the period and the deadline or relative deadline are completely different, then there is a separate procedure. There is a separate mathematical model for this kind of task set. Anyway, we are not going to touch upon that advanced concept. We are going for the basic assumptions. All the tasks in the task set are periodic. The relative deadline is equal to the period. Okay. So generally, this is we called as the assumptions. Now we will come to the rate monotonic. So rate is equal to 1 divided by period. Rate is equal to 1 divided by period. So please remember these formulas. Okay. So the rate equal to 1 divided by period. Rate monotonic means generally higher the rate, higher the priority. That means rate and period are inversely proportional in that case. Lower the period, higher is the priority. Okay, so lower the period, higher is the priority. So generally, if it is a periodic task, there will be periods will be given. So lower the period, higher will be the priority. Okay. So please remember, rate and period are slightly confusing concept. So the period is equal to 1 by rate and rate equal to 1 by period. Okay. So the name of the algorithm is rate monotonic. That means what? Higher is the rate, higher will be the priority. Since period is the data given will be only period. So lower is the period, higher will be the priority. Okay. Okay. Now we will go with one problem, one example we will go with. An example. Okay. So I have a 3 task set. Three task set. Okay. So 1, 2, 3. So the task set T1, T2, T3. So totally 3 tasks. T1, T2, and T3. So name of the task. Okay. I am giving the arrival time. AI is the arrival time. I will just tell you that. So AI is the arrival time. So generally arrival time or release time. Already we have seen this in the last class. Arrival time or the release time. So in this case, so we have AI. We have through 0, 1, and 3. So generally we have 3 things. AI 0, 1, and 3. So then PI is the period. So the period is 2, 6, and 10. EI is the execution time. Execution time is 0.5, 2.0, 1.75. Okay. So example 3 task set. AI is 0, 1, 3. That is arrival release time for T1 is 0, T2 is 1, T3 is 3, and the values are given. Okay. So when we see that whichever the lower period, so the period is lower here. We will just take some other thing. So high priority, medium priority, low priority. I use priority here. Why priority here? The 2, it is low. Next is 6. Next is 10. So that means as per this, we have P1 greater than P2 greater than P3. This is the priority. So P1 have high priority, P2 have low medium priority, P3 have high priority. Now in our case, I'll go with PI is period. Then EI is execution time. Okay. So these are the values there. So execution time is the time by which the task can execute. Okay. Now here somewhere I just forgot to tell you here what is maybe a feasible schedule. What is maybe a feasible schedule? So feasible schedule means okay, all the tasks in the task set have to be scheduled at least once. All the tasks in the task set have to be scheduled at least once. So in that case, we call that as a feasible schedule. So we have optimal schedule, we have a feasible schedule. So that means all the tasks in the task set have to be scheduled at least once. So that is called as a feasible schedule. That means we have now three tasks set with the three values 2, 6, 10 as a period. Then we have to schedule it, and it has to schedule at least once. But what is the duration? So in red monotonic scheduling, so the duration here is we have LCM of period. So that means 2, 6, and 10. Okay, that's LCM. So LCM, how do we calculate? 2, 6, 10 we will calculate. So generally 2, 1, 3, 5, then 3, 1, comma 1, comma 5, then 5, 1, 1, 1. So 5 into 3 into 2, which is equal to 30. So within 30, we have to check whether they execute at least once all the tasks. Okay. So now I will just draw the uh, schedule. Okay. So 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, like that. It will go on up to 30. Okay. So whenever you draw, you put at 30, but we will see whether it is a feasible schedule or not. Okay. But in case if you are planning, then you have to put it up to 30. In case you can reduce the scale also. Now I use 2 at a time, 2, 4. In case if you want to reduce down, you can make 3 at a time. Okay. So to make you understand, I am giving 2 at a time. In case you can have 3 at a time. Okay. So now we will take 3 coloring. Let's say I will take T1 in black color, then T2 in red, and T3 in yellow. I'll take 3 colors. Okay, so T1 will be in black. Now I'm going to T1. So T1, what is the constraint here? T1, uh, the arrival time is 0. That means by time 0, the task is ready. That is T1. But T2 comes only at 1, and T3 comes only at 3. So T3 is releasing only at the time unit number 3. Execution time of T1 is 0.5. Okay, so time period is 2, every 2 times second. So now what I do is, uh, as per this black color, so 0.5 time minutes. So T1, then 2, 0.5, 4 to 4.5, 6 to 6.5, 8 to 8.5, 10 to 10.5, 12 to 12.5, 14 to 14.5, 16 to 16.5, 18 to 18.5, 20, 20, like that 22, 24, 26, 28, 30. So up to 30, it will be running every 2 time units, the task will execute, because the unit is 0.5 only is the execution time. So generally it is 0.5, it is 2.5, it is 4.5, it is 6.5. Okay, so that's how the way it get executed. Okay, now T1 is executed. Now T2 is there. So since it is a static priority scheduling, I need not check every time, so I can able to schedule it, because this static priority I know how to handle this RMA algorithm. So T1 is done. Now T2 the task is, let me take it red color. So the T2, what it says is the arrival time is 1. It is releasing at 1. The period is 6, and the execution time is 2.0. Medium priority. So now what I do is, till one time unit, the task doesn't execute, because up to it releases only by 1. At 1 unit it releases. So what happens? It will be running here. Okay. Now this is T2. What happens T2 here? The execution time is 2 time units, but it can able to run only 1 time unit for time for a time. That is only 1. After that, from 2.5 to 3.5. Okay, so this value is 3.5. Here T2 equal to 1. So 2 time units it completed, because it releases at 1, but it can execute only 1 time unit, because the second version of T1 is coming again, so that this task will be preempted. So this area is called as T2 is preempted by T1. Preemption. So this is where we called as preemption. So the T2 is preempted by T1. That means the T1 have a high priority task. When it comes, the T2 has to suspend that. It stops its execution and give way to the T1 task. Okay. Now after that, after T1 releases, after T1, then T2 again takes the CPU and then run it. Okay. Now this is done. Now at 1 it has come. What is the period here? 6. So 1 plus 6 will be 7. It will be releasing again at 7. 7 plus 6, 13. It will be again releasing at 13. Okay, now in that case, this will run for one time unit. So T2 equal to 1. Then 8.5 to 9.5. Again T2 equal to 1. So totally two time units. Similarly, 13 to 14, one time unit, it runs T2 equal to 1. And 14.5 to 15.5, it runs T2 equal to 1. So two time units. So likewise, after 13, it becomes 20. It releases at 13 plus 6 will be 19. It will be releasing at 19. So 19 means from here to here. So T2, then from there to there, T2. So likewise, the T2 got executed. Next thing is T3. So T3 again will come back here. So T3 we have releasing at 3. Period is 10. Execution time is 1.75. Okay. So in that case, low priority. So what we do is, now 3 means 3.5. No, it releases at 3. Somewhere here 2.52. At this point, it is releasing. So 3.3 at time 3 it releases. So that means 3.5 to 4. So T3 0.5 time units it's completed here. Because 3.5 to 4 only 0.5 time unit it got. Afterwards 4.5 to somewhere here 4.5 to 5.75, that is 1.25 units. So in that case, T3 completed 1.25 units. So totally T3 equal to 1.75. Okay, so that completed. Afterwards, it releases at 3. The period is 10. So 3 plus 10 will be 13. It will be releasing again at 13. But 13 already some tasks are running. So it doesn't get the CPU. Now in that case, it gets 0.25 here. So here it is 0.5. T3 0.5. Then 16.5 to 17.75. So in that case, T3 equal to 1.25. So totally 1.75. Okay. Now I have drawn up to 20 time units. So up to 20 time units, the T1 executed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 times T1 executed. T2 executed 3 times. Sorry, 4 times. Whereas T3 executed only 2 times. So up to 20. So when you extend up to 40, up to 30 time units, then you can see how many times the task get executed. So this is where valid feasible schedule. Okay, so this is what the feasible schedule. That means at least one time the task have executed. But we have a schedulability test. In RM scheduling, we have something called
Sir,
as the, yes.
what if we have a task which is non-preemptible?
No, but assumption is preemption directly. Because real-time embedded systems, most of the tasks will be preemptible. So non-preemptive task generally it is available in a general purpose operating system. Generally, real-time system embedded systems, by default, all the tasks will be preemptive because we have to give priority to the higher priority task have to be have a given good priority. Only then we have a lower priority task. In case priority, if it is a non-preemptible one, then you should not give the CPU to it until it completes. Okay, so
Okay, sir.
as you do in operating system, general operating system, most of the tasks are non-preemptible. So even if you take Linux OS or any OS, most of the tasks are non-preemptive. I mean, all by default it is non-preemptive. So in that case, what you do is till the task completes to the execution, the higher priority has to wait. Okay, but in embedded systems that doesn't happen. Okay, if you take an example of a Tesla car, if you take the self-driving car, if you take, let's say applying brake, when an obstacle comes in front of the car, if that is being controlled by one CPU, and the same CPU controls some other task as well. So now high priority is only for when the car in front of the obstacle, it has to stop. Suppose in that time a low priority task is not giving the CPU and the high priority task is waiting. In that case, no brake will be applied. The car will go and hit the obstacle. So that should not happen in embedded system. That's why most of the embedded 100% of the embedded systems, the task set by default will be preemption. But we have a condition. If non-preemption, what happens? In that case, the task will not be the low priority task does not give away the CPU. The higher priority has to wait. Okay. Okay. So the schedulability test. So how do we find the schedulability test? So we have two conditions. One condition is the necessary condition. So the necessary condition is n into 2 power 1 by n minus 1 should always be less than or equal to 1. So n into 2 power 1 by n minus 1 should always be less than or equal to 1. So in that case, where n is the number of tasks, n is the number of tasks. The other way around, the necessary and sufficient condition. That is Wi of t is less than or equal to tau I. Anyway, we are not going to see that. If we go and check it for schedulability test, it will be a very complicated process. Anyway, I'm just stopping it here for the RM algorithm. So the necessary condition here is n into 2 power 1 by n minus 1 should always be less than or equal to 1. So this is what the formula for this rate schedulability test for rate monotonic scheduling. So mostly when you see the number of tasks, now in our case, what happens? This task 3 into 2 power 1 by 3 minus 1. So that means 2 power 1 by 3 will be 0.73 something, 0.7 minus 1, not 0.7, 1 point something, cube root of 2. Anyway, I'll just show you a graph also for that. So it will be always be less than or equal to 1. So your graph will be coming like this. Okay, so it will be 1.0 and is somewhere from 0.8 to 0.6. So even if you go up to 10,000 tasks, the value doesn't change. It will be coming like this. So for this formula, okay. So that means the schedulability test will always be true when the number of tasks are going high. Okay, so will always be less than or equal to 1. Okay, so this is what the schedulability test for the RM algorithm. Okay, so next one is we have EDF schedule. EDF, earliest deadline first. So EDF algorithm. So EDF algorithm says that, as the name says that, uh, earlier the absolute deadline, higher the priority. Higher the priority. Okay, so we have again two deadlines, absolute deadline and relative deadline. We have two values there. So DI is absolute deadline. DI absolute deadline. The small DI will be relative deadline. So the formula will be DI equal to DI minus AI. So that means the relative will be equal to absolute minus arrival time. Arrival time or release time. So which are I'm just using arrival time here, but release time RI can also be taken. Okay, this we have already seen in the yesterday's last class discussion. Okay, now we'll go through one example on this EDF. EDF is can be easily thing, but EDF is a dynamic priority algorithm. Every time minute you have to check the deadline. So only then you have this option here. Okay, so I'll just show you that. So T1, T2, T3. So arrival time we have 0, 4, 5. Then we have EI is 10, 3 and 10. And we have absolute deadline, we have 30, 10 and 25. Okay, so we cannot have priorities fixed during compile time, because the initial time priority we have to check it. Okay, so we have to check the priority every time unit, we have to check it. Okay, now let me draw the here there is no LCM here, because we are not going to compile everything, so everything will be happening at the runtime. So the system scheduler designs how this can be done. So for the sake we I just take it from 0 to 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, like that. Okay, so There is no limit on that. I can able to draw as many things as possible, but only in the RM scheduling, since it is static priority, we will be doing all the design before the system starts. So that's why we use the LCM of all the three values. Okay. So now at time 0, let me check it at time number 0. At time number 0, only one task is ready. So that is T1 is ready at time number 0. So what I do is the execution time of T1 is 10 time minutes. So what I do, up to 1 I'll try. At 1 time minute I'll check it. Any task is ready. No one is ready. Then I'll extend to 2. At 2 time minutes anyone is ready? No. Then extend to 3. Nobody. And extend at 4. Then at till the time I have T1. So T1 is running up to 4 time minutes. At 4 time minutes, what happens is time number. I mean, this is what the T2 now. At T2 comes at time minute number 4. That means at 4 time minutes T2 releases. Now at this junction, T2 versus T1. So T2 versus T1. Now T2 have earlier deadline. That is only 10 time units. The deadline is only 10. Whereas the deadline for T1 is 30. So 30 and 10 it is compared. So it is something like, I will tell you an example. If you are going in big bazaar, a supermarket, you are with a trolley. Okay, so now you are waiting with a very big trolley on a counter to get your things built. And in front of you, there is one other person with a very big trolley. So both are waiting in the queue. Now there is one person coming. He is taking only two products, one Coca-Cola and one chocolate, a chocolate and a soft drinks. He has brought only two. Now he is searching for that and he is coming and asking you, sir, only two things to be built. Can I please go ahead? You are telling that you are having a very big baggage, but your time will be taking so much time. Next is you. So in that case, what happens? Okay, you give the CPU to him. Okay, no problem. You carry on only two. Okay, but in embedded system, what happens is, if you are already been evaluated your product, if a new task comes with the earlier deadline, you will be stopped. That means you will be stopped in between, and that task will continue. So till that time, you will be suspended or preempted, what we call. Okay. Now T2 versus T1. So T2 have more priority than T1 because the deadline is earlier. So in that case, T2 runs now. At 5 time unit, one other task is ready now. At 5 time unit, T3 releases. Now at time unit 5, T3 versus T2. Now when say T2 and T3, again T2 is outperforming T1, T3 because the deadline is earlier than T3. So then T2 continues till 7. So T2, 4, 5, 6, 7 completed its job. Okay. Now at this point, the time unit number 7. At this point, we have two tasks ready, T3 versus T1. We have two tasks ready, T3 versus T1. In that case, what happens? T3 have 25 deadline and T1 has 30 deadline. So now still the earlier deadline will be for T3 only. So T1 has to still wait. So in that case, from 7 up to 10 time minutes, 17 up to 17, T3 runs. After 17, T2 continues. So T1 continues. So T1 already 4 time minute over. 17 plus 6 will be 23. Sorry, in black color, no? So T1 runs. Okay. So T1 completed at 23. Though it released at 0, but it completes the CPU only by 23. Okay. So that means T1 is a low priority task. It has to keep on waiting whenever there's a new task comes there. Okay. So now here it is a preemption. Then that's all. So only one time there is a preemption, and T2 doesn't happen anything. So here also there is a preemption. So preemption is not here. After T2 completes, T3 take over because the CPU is compared. So preemption is happening only one time at this particular thing. But it is quite obvious that we can compute the waiting time. So average waiting time. So average waiting time. So that means waiting time of T1 is what? So T1 released at 0. Okay, so T1 released at 0. It completes at 23. Okay, but waiting time in how long it was waiting. So from 4 time minutes to 17 time units it waiting. So T1 was waiting from 17 time units minus 4 will be 13 units. So 13 time units T1 was waiting because 0 to 4 it was running. So it is not waiting time, it is running time. But for till it get the next time when they get the CPU, it takes only at 17. After 17 it is running. So running we don't calculate, only the waiting time. So from 4 to 7, 4 to 17 it was waiting. So totally 13 time minutes. The waiting time of T2 is, so T2 it released at 4 and immediately got the CPU. It never waited. So that means 0. T3 it released at somewhere at 5. It released at 5, but when it got the CPU, it started running only by 7. That means 7 minus 5 will be 2. Okay, so average waiting time will be 13 plus 0 plus 2 divided by 3, which is equal to 5 time units. So the waiting time of all the tasks, average waiting time will be 5 time units. So sometimes the embedded systems can able to measure the performance of average waiting time. So that means how long the tasks were waiting in the queue because of preemption. Okay, so this preemption, this is how the way it waits. Okay, but we have a good factor here, U, utilization factor. Utilization factor. Generally we call as a CPU utilization factor, which is equal to sigma EI by PI, which should be less than or equal to 1. Sigma EI by PI, which should be less than or equal to 1. So that is what one condition here. But mostly now in our case, when we see EI by PI, PI is a period. PI period. So generally we have seen that PI will be equal to relative deadline. For our assumption that the relative deadline is equal to the period. So relative deadline means absolute deadline minus the release time. So now in this case, TI will be 30 minus 0, 30, 10 minus 4 will be 6, 25 minus 5 will be 20. So that is 30 minus 0 will equal to 30, 10 minus 4 equal to 6, then 25 minus 5 equal to 20. This is the relative deadline. So now when we see EA by PI, that means 10 by 30 plus 3 by 6 plus 10 by 20. So you can see here 10 by 30 plus 3 by 6 plus 10 by 20. So you can see the value 1 by 3 is 0.33 plus 0.5 plus 0.5, which is equal to 1.33, which is greater than or equal to 1. So in that case, the CPU utilization is going up to 133%. So 133% of CPU is been scheduled, which is which feels that the EDF is not a I mean EDF takes more amount of time for the CPU time to execute this task set. Okay, so this is how the way the utilization of the CPU will be calculated. So this is one factor, but it is not a necessary condition or anything. It is just a factor to determine how long will be the CPU will be affected. But in reality, generally most of the task will be in milliseconds, microseconds, and nanoseconds. Okay, the period also will be very fast enough so that 10 tasks will be running at in one CPU. So we will have multi-process scheduling. So we have many multiple processor. They can share the load between the multiple processors.